Hello, yeah. In this video, I will show you how to perform a kernel principal component analysis using R. The kernel principal component analysis is an extension of the traditional principal component analysis. It's designed to handle nonlinear data relationships. The primary purpose of KPCA is to perform dimensionality reduction and this approach allows KPCA to capture complex nonlinear patterns in the data, making it particularly useful for tasks such as image and speech recognition, where traditional PCA may fail short. Okay. So to do KPCA in R, we need a R package called a Kernel. Okay. So I already installed that here. So let's load in the kernel lab into the RStudio session, set the random seed. So we have 100 data points. Now let's generate two variables, x1 and x2. They're all from normal distribution. One is mean 3, standard deviation 1, and the other is mean -3 and standard deviation 1. Okay, so we can combine these x1, x2 into a matrix for the data, and then we create a third column, which is the first column squared plus the second column squared. So the third column is a nonlinear function of the first two columns. Okay, and we force it into a data frame. And we call the column names as feature 1, feature 2, feature 3. And remember, feature 3 is a nonlinear function of feature 1 and feature 2. Okay. So to perform kernel PCA, we use the R function called the KPCA. And if we are using all the variables in the data frame, we're just simply using here dot that will include all the variables. Okay? And data equal to data underscore df. And we'll use the kernel option. There's multiple choices for this kernel argument. We're going to use this RBD dot, so it's a radial basis function kernel, and we can specify a hyperparameter called the kpar equal to list sigma equals 0.1 here. So here you can use different sigma values. For example, you can use 0.2, 0.3, or 0.05. Okay, so you can experiment with the sigma value. You can see how the result changes. And maybe you can even, do a hyperparameter optimization. So let's just create this output. It's pretty fast. And now let's examine the result. First, let's extract the principal components. We use rotated parentheses KPCA underscore result and put it into a data frame called the PC underscore data. And then we name this as a PC 1 or 2, 3, etc. Okay. And then we can plot out the first component. So this is the principal dimension. You can see the data can be clustered, into two clusters. The red colors versus the blue colors, they obviously clustered separately. And if you really want to see which observation each dot is, we can use this additional line of command to assign the labels of the number of observations to each data point. Okay, so, and then another thing is we can do is to look at explain the variance. So we have to extract the eigenvalues from that KPCA result. And there's a component called EIG, that's the eigenvalues. And the explained variance is the eigenvalues divided by the total sum of eigenvalues. So we can print out explained variance. You can see we have total of 83 components. Okay, so you may ask, we have 100, I think how many, more than 100 or data points. Why we have 83 components? So the reason is that when we perform the kernel smoothing, the kernel function, the kernel matrix is usually not full rank. So these 83 should be less than 100. Okay, and from this result, you can see the contribution, the variance explained by each component, listed from the largest to the smallest. So for this one, each component explained a little bit variance. Like the first one, component 1, explained about 10%. Component 2 explained 8%, etc. Okay. So if you want to decide how many components we want to represent the data, so usually we want the cumulative explained variance to be greater than 80%. Okay, so we can calculate the cumulative variance and then print it out. If we look through it, it's about, I think, component, let's see, yeah, about component 19, where the cumulative variance exceeded 80%. Okay, so this is a tutorial shows you how to quickly perform a kernel principal component analysis using R. Yeah, there are much more details in the documentation, so please spend some time to read through the documentation to learn more options you have in using this function called KPCA. Okay. All right. Thanks for watching.